Hi, this is Keenan Casey for Tuts Plus. In this lesson, we're going to be talking about decision trees. Decision trees are really very simple. They're really just a sequence of tests where you answer a question and then follow a branch until you get to the bottom of the tree. We're going to see how these trees can be constructed. We'll also discuss some techniques for improving the performance, pruning, and consider some variants on how to create decision trees. Here are some important terms we need to understand before we start. First, we have the input to our decision tree, which is going to be called X, which is a vector. Our output is going to be a class, so that could be geek or non-geek based on the example that we've been using. Furthermore, we're going to be creating trees visually. We're going to have a root node at the top. That's going to be a rectangle. There'll be decision nodes where questions are asked. Those will also be rectangles. And there'll be leaf nodes, which are ovals, and those are at the bottom of each branch. So what we see is that the root nodes are the first decision. Each subsequent node is a decision node where a branch or split takes place, and then at the bottom of the tree we'll have our output, our classification Y. And let's begin with an example of how to use decision trees using our geek data set. First, we start at the root. We answer a question, we follow the split based on the answer to that question, and then we repeat until we're on a leaf node. For example, we might first ask, how many programming languages does this individual know? If it's 0, we'll go one direction. If it's 1, take another branch. If it's 2 or more, we'll take this third branch. If the person knows 0 programming languages, we'll say they're a non-geek. And if they know more than 2, then they're a geek. Now, if it's just 1, we'll ask another question. So we'll have another decision node. In this case, GPA. Is GPA less than 3.6? If so, they're non-geek. Is it greater than 3.6? Well, we're going to ask another question. Our next decision is, do they prefer Star Trek or Star Wars? If they choose Star Trek, then we'll say they are a geek. If they choose Star Wars, then they're a non-geek. So this is a decision tree that's been created, and we've seen how to use it. The next thing we need to consider is, how do we actually construct one of these decision trees from a set of data? So these are the 3 steps in creating a decision tree. First, we're going to find the best feature to split on. There are several ways of doing this. One way is using a measure called entropy, which is related to information gain. This is the equation for entropy, and entropy is really just a measure of how much uncertainty there is in a set of data, how mixed up the data is. So if a data is more mixed up, it has more entropy, and this is based on information theory. What we're going to do is measure the entropy of the original data set and the entropy of each possible split and choose the one that reduces the entropy the most. That way we found sort of the most information-full split. And this measurement of what gives us the best split using entropy is called information gain. This entropy equation uses the notation P of X, where that is the percentage of the instances that meet a certain class. There's another metric that's used to choose the best feature. In some algorithms, it's called the Gini index. This is a way of determining the impurity of a set. So it's very similar to entropy, but it's a different way of computing it. And this is the formula for the Gini index. So using one of these methods, we're going to find the best feature, the best column in the data set that we should split on. Next, we're actually going to split those instances using that feature. What that means is we're going to create a new branch and divide the instances using that rule that we've just found. Thirdly, we will repeat. So that means we're going to recursively go down and do the same thing again until we're done. What does done mean? Well, done may mean different things. It may mean there are no more features that we can use for creating branches. If all of the instances are the same class based on the decision tree that we've created so far, then we've succeeded. And we'll stop there and create a leaf node that is that class. Or if there's no majority class, if there's a tie, then we need to stop because we really can't make any classification decisions at that point. I wanted to give you an example of how to compute entropy and information gain on a really simple data set. So let's assume that we have 8 instances in our geek, non-geek. We have 3 features, which are programming language, GPA, and the Star Trek or Star Wars preference. Let's consider the data. The first split is if the number of programming languages is 0. You can see in this case we have 0 of the geeks match that rule and 8 of the non-geeks match that rule. If we split based on GPA, if GPA is, say, less than 3.6, the geeks, we have 2 instances that match that rule, the non-geek 6, And if we split on whether they prefer Star Trek, that's split right down the middle, 4 geek, 4 non-geek. All right, well, let's compute entropy using this data. In programming languages, we compute P of geek, which is 0 out of 8. The probability of non-geek is 8 out of 8, which is 1. This is the formula for entropy for the geek, non-geek using programming languages split, and that reduces to 0. Let's do the same thing with GPA, where the probability of geek is 2 out of 8. Probability of non-geek is 6 out of 8. Substituting that in the formula, we get this value 0.813. Lastly, with the Star Trek, Star Wars, we've got these two probabilities, both 0.5. Substituting those in the equation, we get a value of 1. So it's clear to see, we saw this intuitively, but now we're seeing it with this formula as well, that the best split is the programming languages split because it has the lowest entropy. There are many decision tree algorithms that make different choices on how to construct the decision tree. One of the simplest, and the one that we're going to look at, is called ID3. And this is how ID3 works. It's a recursive process, so we're going to define a function called createTree, which takes in some instances and features, and we will call createTree from createTree. First, we're going to create a root node, which we'll call R. We'll then test to see if all the instances are in the same class. If they are, then we found a really good way of dividing this data. We're going to return R as a leaf node with that class. Otherwise, we're going to also check to see if all the features are used. If we've used all the features in the data set, then we're also done, and we'll return R with the class that is the majority. Now, those are the two special cases that end the algorithm. This is what we're going to do most of the time when we're constructing it. First, we're going to find the best feature. That could be using Entropy or Gini. ID3 uses Entropy. For each value of the feature that is the best, we're going to iterate through this and determine what instances have that value. If the set of instances is empty, then we're going to return our root node with a class that's the majority class. Otherwise, we're going to create a new branch based on the instances that match, and we're going to pass in the set of features without the best feature that we found. So now there'll be one less feature than we had when we created this branch. We'll add that new branch to the root branch and continue. So what we see here is that this createTree function is calling itself. So we keep recursing down, dividing and subdividing the set of instances until we have only leaf nodes, only the bottom, and that recursive tree that we've created will be used to do our classification. This is the ID3 algorithm. Now, the problem with decision trees is they get big and they get complex. And when we get really large trees and really complex trees, they often will overfit the data. They'll just end up memorizing the data instead of understanding the underlying pattern. This is an interesting example. This diagram shows the optimal placement for the O player. And what you can take away from this is how complex this decision tree could become. And this is plotted in a pretty compact way. So the problem of decision trees is overfitting. How do we address that problem? The solution is tree pruning. And that means removing branches. Simply put, we're going to take off the branches if they're overly specific and don't really help the model predict well. One way to do this is to calculate errors associated by merging two leaf nodes together. And if that doesn't have a bad impact on performance, then we'll merge them together to make the tree more general. There are a lot of ways to create a decision tree algorithm, and there are many decision tree algorithms out there. I wanted to try to encapsulate this by showing some types of variation that decision tree algorithms possess. For one, the type of feature selection measure that's used. We've seen you could use information gain or the Gini impurity index. Another option is the feature set removal. Some algorithms don't remove features when they're used from the set of features. ID3 did, C45 does not. Another variation is whether regression is possible. Some algorithms like CART allow for regression, and they use mean and variance in order to do feature selection instead of the information gain or Gini. Another option is the number of splits. In ID3, we can actually split multi-way, more than two, whereas with CART and C45, you can only have two splits, a binary split. And lastly, the structure of the leaf itself. We've seen leaves that are just the class label that would support classification. It's possible to actually, in the leaves, have a linear model. So you have this formula that is the end result of the leaf that actually takes in the input and does a little bit of math to produce the output. This is a summary of the strengths and weaknesses of decision trees. They're cheap, inexpensive to use computationally. They're really nice because you can understand them and interpret them. In fact, this is really important for some decisions because it's a legal requirement. Some financial loan decisions are protected by anti-discrimination laws, so you have to be able to explain why the computer said no. Decision trees allow this. Other methods like neural networks have no interpretability. A couple other nice parts about decision trees is that they can handle missing values in the data set, and if there are features that are irrelevant, they can handle those also. The weaknesses of decision trees are that they're really prone to overfitting. They really can memorize a data set and fit it too precisely and not generalize. Also, their greedy choice of attributes to use is not optimal, but most algorithms have to work that way so that they're tractable. And lastly, they're very much limited to the range on the training data. So it's not possible to predict beyond the minimum and maximum limits of the input variables that you use in your training data because the decision tree has no idea what to do with those large and small values. How do decision trees fit into our representation, evaluation, optimization, three components of machine learning? Well, the representation is this tree structure, which we've seen. In terms of evaluation, we could look at the sum of squared error or the classification accuracy, as we've seen before. What is the percent correct that are accurately predicted? And lastly, how do we optimize? We saw two things. We could prune or we could stop early, which is really a form of pruning. Remove branches that are highly specific that really don't help us that much. So this has been a look at decision trees, which are a classification and regression algorithm, a part of supervised learning. I'm Keenan Casey for tutsplus.com. Thank you for watching.